So this video is going to be about vectors and lines. So first we're going to start with two different types of vectors. The first vector is a vector called a normal. It is a vector which goes perpendicularly to something else. So in this case, this normal vector is perpendicular to this line here. And then there's also directional vectors, which are vectors that can go in a specific direction and can also be parallel to a line. So, for example, this vector here and this vector here are both directional vectors of this line because they are both parallel to the line. One special thing you can do with directional vectors is you can essentially have a vector which has a value of 1 as its x step, and when you do that and it's a directional vector, the y step will always be equivalent to the gradient of the line that the directional vector is a directional vector of, or parallel to. So as you can see here, this vector has an x step of 1, and its y step is equal to the gradient of the vector because to the gradient of the line because the vector is parallel to the line. This means that you can also translate the equation of a line into a vector, or into a directional vector. So as you can see here, we have this equation of a line, which is y equals 2/3 x plus 3. Essentially what you want to do is you want to take the vector which has an x step of 1 and a y step of the gradient, and you input the y step of the gradient, or the gradient, into the y step. And then you also multiply by the c value because you are moving the vector to be on top of the line. So here this vector, or the vector of the directional vector of this line, will be 3 times the vector 1, x step of 1 and y step of 2/3. And because 3 multiplied by 1 is 3 and 2/3 multiplied by 3 is 2, this will then be the vector equation of this line, or the directional vector equation of this line here. So next is the vector equation of a line. So here we have a normal vector to this line, and we have this line, which also has another vector, a directional vector on top of it, and all of these are of course arbitrary. This vector n is the normal, and this vector here, this vector AB is the directional vector. Take the equation of a line and we try to end up with that using what the knowledge we already have about vectors. So we start with vector AB multiplied by the normal of the line and set that to be equal to 0. Using the rules of multiplying vectors, we multiply these together, so we get this here, and then we essentially use the distributive law and apply it here. Here we essentially organize it into n1x plus n2y plus negative x 0 n1 minus y0 n2 equals to 0. This here can then be put into a constant or a scalar, because this is essentially where this vector is on the line. This is the scalar of this vector. Meanwhile, this here is essentially the vector equation. So this here would be the vector equation of this line. And as you can see, this looks like the normal equation of the line, or the general equation of the line, because we have n1, which is our a value, and then we have x, and then we have n2, which is our b value, and y as our x, and c is our scalar, just like k is here, and then equals to 0. Here we can essentially say that a is equal to n1 and b is equal to n2. So using that information, we can take any equation for a line, and we can use the equation for the line to find the normal to it. So for example here, 3x plus 4y minus a equals to 0. We can easily identify n1, which is a here, and n2, which is 4 here, so, or b here. So we essentially just put the numbers into the vector equation, and we end up with a normal, which is equal to 3, 4. Next, we have using vectors to find angles between lines. So we can use this formula to find out what the angle between two vectors is. Its cosine of an arbitrary angle equals to vector A times vector B divided by the length of vector A times the length of vector B. So here we draw an example of two lines intersecting where we want to find the angle between the two lines. Now we want to find the angle between the two normals and the two directional vectors. So we put them up together next to each other as seen here and as seen here. Next we want to find out what the angle between these two are, because as you can see the two directional vectors angle is equivalent to the angle between these two lines. It's equivalent to the acute angle of these two lines. And you can see that because the directional vectors are essentially parallel to the lines, meaning that the angle between them is exactly the same. What you'd also see is that the normals of these directional vectors are essentially the directional vectors, but rotated by 90 degrees, since the normal is a perpendicular vector to the directional vector, meaning that the angle between the two normals will also be the same, since they're both rotated equally, which is by 90 degrees. And this means that you can also put in the values for the two normal vectors to find out what the obtuse angle of these two intersecting lines are. So when we do that, we can see that with this example here, we're going to have the two lines 2x plus y equals to 5 and 2x minus 3y equals to 18. And using the information we learned before, we can see that the n1 here, the x step for it is 2x, so the x step is 2, and the y step is 1. And for n2, we can see that the x step is 2 and the y step is negative 3. So what you want to do then is just put in the values into the formula. So we're going to start by multiplying n1 by n2, which is equal to 2 times 2 plus 1 times negative 3, which equals to 4 minus 3, which is equal to 1, which is why we have a 1 up here. And then we want to find the lengths of n1 and n2. And here we simply use Pythagoras with the x step and y step as our cathetes, while our result is going to be our hypotenuse, which is the length of the vectors. So what we do here is we just 2 squared plus 1 squared equals to the square root of 5. Or the square root of 5 will be what we're going to put input here. And we do the same thing for n2, so we end up with the square root of 13 to input. And to find the angle, we essentially take the inverse cosine of 1 divided by the square root of 5 times the square root of 13, which is then equal to 82.9 degrees as the angle between these two lines. If you're looking to find the obtuse angle of a line, you can look here. You can see that the obtuse plus the acute angle is equal to 180 degrees, meaning that if you subtract 180 by the angle that you calculate, you can find out what the obtuse angle is. So for example, the obtuse angle of these two lines here would be 97.1 degrees. Next we have vectors and perpendicular and parallel lines. This is quite simple. Essentially, if a vector is parallel to a line, it can be expressed as one vector. If you have two vectors, one can always be expressed as the other, but with a scalar to it. And for perpendicular vectors are only perpendicular if the two vectors multiplied together, or the dot product, is equal to 0. So here, for example, we have vector A times vector B, and if you multiply these two together, you end up with 2 times 2 plus 2 times negative 2, which equals to 4 plus negative 4, which is equal to 0. That is supposed to be 0. So next we have deriving the vector equation of a line. Essentially what that means is that you want to find the vector equation of a line by using other vectors. And we have vector r here, which is going to be our tool to find the vector equation of this line. Essentially, vector r is going to be vector OP plus vector PQ, as you can see here. Vector OP plus vector PQ is equal to vector r. And the way you find this out is you essentially take the vector for point P plus a scalar times the vector PQ. And vector PQ is essentially x minus x0 and y minus y0. And essentially, k is a scalar, which can help you put vector r pretty much anywhere on the line. Because vector PQ is the vector equation for the line, and vector PQ can be wherever you want it to be on the line. So this scalar is the tool you use to find or to place vector PQ wherever you want it to be on the line. So lastly, we have how you would convert the vector equation into the standard equation of a line. So here we have a standard equation of a line. To make it easier on ourselves, we're going to turn that into the slope-intercept equation of a line, as you can see here. And here we have the vector equation of a line, and we turn that into the vector equation of a line the same way as we see it here. So we have this here is our point, and this here is our directional vector, and this here is our scalar. So the way you convert the two is essentially you can set x to be equal to 1. It can be whatever you want, but 1 is the easiest. Or you set the x step to be 1. And next you essentially do the formula up here where x is equal to 1. So you set what y is equal to if x is equal to 1. So in this case, with this arbitrary formula, y will be equal to AC divided by B. And next you have the directional vector part of it, and the way you translate that is essentially you again set x to be equal to 1, and then the gradient, because the directional vector will always, if the x step is equal to 1, then the y step will always be equal to the gradient, as we learned before. So using an example here, we have this line formula here, a line equation here. 1x plus 1y equals to 3 is a really simple one. If you translate this into a slope-intercept, you end up with y equals 3 divided by 1 minus x divided by 1, which you then can translate into y equals 3 minus x, and then gets translated into y equals negative x plus 3. Now what you do is, as explained here, we want a point here, so that there is going to be 1x, x step of 1, and y, if you take an x step of 1, then y is going to be equal to 1 times negative x plus 3, so you end up with negative 3 here as our y step. And then for the gradient, you essentially set the x step again to be 1, and as you can see, our gradient is minus 1x, meaning that our y step is going to be negative 1 as well. And of course, this also works the other way around. So as you can see here, if you wanted to take this vector equation and put this into a line equation, you would just realize that this here, the top part is going to be connected to the bottom part. So the easiest way to do this is by dividing the x step into being 1 in some way, and finding out what the factor is to turn the x step into this y step here, and that will give you what is supposed to be up here as what's on the right side of the equation. And over here, what you essentially do is, again, you want to reduce this into being 1 in some way, and then you will automatically have the gradient down here.